NENOMATICA, where mathematics meets YouTube excellence. Welcome! We will extract, structure, and teach the idea of the characteristic and mantissa of common logarithms, the characteristic of a logarithm. Step 1. Observe base 10 logarithms of powers of 10. We recall the rule for the definition of a logarithm. Now, pay attention to these two numbers. 100 equals 10 squared, therefore log of 100 equals 2, and 1000 equals 10 cubed, therefore log of 1000 equals 3. Step 2. Determine the range for numbers between powers of 10. Since the logarithm with base greater than 1 is increasing, if it is less than c, log base 10 of a is less than log base 10 of c. Therefore, if a number n lies between 100 and 1000, its logarithm lies strictly between 2 and 3. Quick challenge. If n equals 500, what is the characteristic of log n? Step 3. Define characteristic and mantissa via an example value. We decompose a common logarithm into integer part plus decimal part. For instance, if log of 200 equals 2.30103, then the integer part 2 is the characteristic, and the decimal part 0.30103 is the mantissa. Step 4. State the sign rule for characteristic and mantissa. By convention, the mantissa is always non-negative and less than 1. The characteristic can be positive, negative, or 0, but the mantissa is always positive. Step 5. Define the common logarithm. When the base is 10, we usually omit writing the base. Log n means log base 10 of n. Step 6. Specify the scope of our discussion. The domain for a logarithm requires the base positive and not equal to 1, and the argument positive. Here we consider base 10 and numbers n strictly greater than 1. Welcome! In this lesson, we will follow, step by step, the exact algorithm for finding the characteristic of a logarithm. We will mirror the structure shown in the reference image, and we will keep the steps in the exact same order. Step 1. First, determine between which two consecutive integer powers of the number n lies, assuming it is greater than 1. Step 2. Because it is greater than 1, the logarithm with base a is increasing, so applying log base a preserves the inequality. Step 3. Use the power rule for logarithms to bring down the exponents n and n plus 1. Step 4. Because the log of the base equals 1, we can simplify by replacing log base of a with 1. Step 5. Split the logarithm into its integer and decimal parts. The integer part, n, is the characteristic, and the decimal part p with 0 less than or equal to p less than 1 is the mantissa. The image writes this compactly as n.p. Important note, if the base is between 0 and 1, log base is decreasing, so all inequality signs reverse in steps 2 and 3. Final statement. The characteristic of log base of n is the unique integer, n such that a to the n is less than or equal to n and n is less than a to the n plus 1. We will extract the characteristic of two logarithms by following the exact step order shown, first for log base 3 of 500, and then for log base 3 of 1/10. First, show the example banner, then the bold orange problem statement. Problem 1. The characteristic of log base 3 of 500. First, use the bounding powers rule for characteristics. Step 1. Find consecutive powers of 3 that bound 500. Compute powers of 3 until we bracket 500, then write 3 to the 5, less than or equal to 500, less than 3 to the 6. Step 2 uses the monotonicity of logarithm. Base greater than 1 preserves inequality. Apply log base 3 to each part. We obtain log base 3 of 3 to the 5 is less than or equal to log base 3 of 500, which is less than log base 3 of 3 to the 6. Step 3 uses the power identity, log base of a to the x equals x. Simplify the ends of the inequality. This yields 5 less than or equal to log base 3 of 500 less than 6. Step 4. Read the characteristic. The integer part is 5, so we write log base 3 of 500 equals 5.p. State the result in green. Now for problem 2, the characteristic of log base 3 of 1/10. Start by bracketing 1/10 between negative powers of 3. Compute 3 to the minus 2 and 3 to the minus 3. Then write 3 to the minus 3 less than 1/10 less than 3 to the minus 2. Start by bracketing 1/10 between negative powers of 3. Compute 3 to the minus 2 and 3 to the minus 3. Then write 3 to the minus 3 less than 1/10 less than 3 to the minus 2. Step 2 again applies monotonicity of logarithm with base greater than 1. Taking log base 3 of each term gives log base 3 of 3 to the minus 3 less than log base 3 of 1/10 less than log base 3 of 3 to the minus 2. Step 3. Use the power rule again to simplify the ends. We obtain negative 3 less than log base 3 of 1/10 less than negative 2. Step 4. Read the characteristic carefully. Since the result is between negative 3 and negative 2, the characteristic is negative 3. Using bar notation, we write bar 3.p, meaning only the integer part is negative and the mantissa is positive. State the result in green. Finally, present both answers together. Wrap up with a short mantissa is positive. State the result in green. First, we display the word example, and right below it, the problem statement in bold orange math. We start with the first expression. We will bound the number 100 between two consecutive powers of 1/2. Then apply logarithms with base 1/2, remembering to reverse inequalities because the base is between 0 and 1. Next, we simplify the negative powers of 1/2. This turns them into powers of 2. Now, apply logarithm base 1/2 to each part. Because the base is between 0 and 1, the inequality reverses. Use the power rule of logarithms. Log base of a to the n equals n. Since 2 equals the reciprocal of 1/2, the results are negative integers. Therefore, the characteristic, the integer part, is negative 7. On old-style logs, we write this as 7 with a bar. Now, we follow the exact same algorithm for the second expression. Rewrite those as powers of 3 with negative exponents. Apply logarithm base 1/3 to each part. Because the base is less than 1, inequalities reverse. Now, simplify using the power rule. Therefore, the characteristic is 2. Quick challenge. Can you predict the next step if the base were 1/4? Take a moment to think about how the inequality direction behaves when the base is between 0 and 1. To wrap up, let's summarize the key ideas and the two results we obtained. Example: if 3 log x equals 2, between which two consecutive integers is x, we will follow the exact sequence of steps from the image. Step 1. Start with the given equation, 3 log x equals 2. Step 2. Use the power rule for logarithms. Move the coefficient 3 into the logarithm as an exponent. This produces log of x cubed equals 2. Step 3. Express the constant 2 as 2 times log 10, since log base 10 of 10 equals 1. Step 4. Apply the power rule in reverse on the right side. 2 log 10 becomes log of 10 squared. Step 5. Compute the exponent. 10 squared equals 100. Step 6. Use the one-to-one property of logarithms. If log of a equals log of b with the same base, then a equals b. Therefore, x cubed equals 100. Step 7. Compare 100 with perfect cubes. 4 cubed is 64 and 5 cubed is 125. So 100 lies between them. Therefore, x lies between 4 and 5. Final answer: x is strictly between 4 and 5. Summary: we followed the exact sequence. Given 3 log x equals 2. Power rule to get log x cubed equals 2. Rewrite 2 as 2 log 10. Power rule again to log 10 squared. Evaluate to log 100. Use one-to-one property to get x cubed equals 100. Compare cubes to conclude 4 is less than x, which is less than 5. Try a quick practice. Solve 2 log x equals 3 and locate x between two consecutive integers. We will solve the problem exactly following the structure in the provided image. First, We display the example and the question, then proceed step by step with rules. Step 1. Set up the inequality exactly as shown. We need the nth root of 0.025 to be greater than 0.5. Step 2. Take the common logarithm of both sides. Because the base is greater than 1, the inequality direction remains the same. Step 3. Use the power rule for logarithms and convert decimals to fractions. 0.025 is 25 over 1,000, and 0.5 is 5 over 10. Step 4. Simplify the fractions. 25 over 1,000 is 1 over 40, and 5 over 10 is 1 over 2. Step 5. Note that the logarithm of 1 over 40 is negative because 1 over 40 is between 0 and 1. Dividing by a negative flips the inequality. Step 6. Both sides are positive, so taking reciprocals flips the inequality again. That gives us n is greater than log of 1 over 40 divided by log of 1 over 2. Step 7. Rewrite the arguments as powers of 2 and 10. 1 over 40 equals 2 to the power of negative 2 times 10 to the power of negative 1. 1 over 2 equals 2 to the power of negative 1. Step 8. Expand using product and power rules for logarithms. Step 9. Since we are using common logarithms, log 10 equals 1. Step 10. Multiply numerator and denominator by negative 1 to simplify. Step 11. Substitute the given value. Log 2 equals 0.3010. Step 12. Compute the numerator. 2 times 0.3010 plus 1 equals 1.6020. Step 13. Perform the division to get approximately 5.32, which the source rounds to 5.3. Step 14. The smallest integer greater than 5.3 is 6. Therefore, n is at least 6. Summary. We set the inequality, applied logarithms, carefully handled the sign flip when dividing by a negative logarithm, rewrote using powers of 2 and 10, substituted log 2 equals 0.3010, computed, and chose the smallest integer, 6. Try this for practice. If log base 10 of x equals bar 18.5365, between which powers of 10 does the fourth root of x lie? Reminder of the characteristic rule. If it is greater than 1, and log base of x equals n point p, then a to the n is less than x, which is less than a to the n plus 1. Step 1. Apply the power rule for logarithms. The log of x to the 1/4 equals 1/4 times log of x. Step 2. Substitute the given value. Replace log of x with bar 18.5365. Step 3. Separate the characteristic and the mantissa. By convention, bar n.p means negative n plus p. Step 4. Adjust the characteristic so division by 4 is clean. We change negative 18 to negative 20 and add 2 to the mantissa. Step 5. Now divide each part by 4. Step 6. Convert to bar notation. Negative 5 plus 0.6341 means bar 5.6341. Step 7. Use the characteristic to bound the value. If log of y equals n point p, then 10 to the n is less than y, which is less than 10 to the n plus 1. With n equal negative 5, we get the final inequality. Use the characteristic to bound the value. If log of y equals n point p, then 10 to the n is less than y, which is less than 10 to the n plus 1. We will solve one example, step by step, following the exact structure shown. Then we will compute the precise range of a. Here is the problem statement. Step 1. Apply the negative exponent rule. X to the power negative 1 equals 1 over x. Then rewrite it using fractions. Step 2. Use the reciprocal form of the change of base. 1 over log base of b equals log base b of a. Apply it to both terms. Step 3. Combine same base logs with the product rule. Log base b of x plus log base b of y equals log base b of x times y. Combine the two terms. Step 4. Multiply 2 times 5 to get 10. Now we determine the range of a. We bracket 10 between nearby powers of 3. Then write the inequality. Because the base 3 logarithm is increasing, we can take log base 3 of each part without changing inequality directions. Apply it. Simplify the ends using log base between nearby powers of 3. Then write the inequality. Because the base 3 logarithm is increasing, we can take log base 3 of each part without changing inequality directions. Apply it. Simplify the ends using log base b of b to the x equals x. This yields a clean numeric bound. Finally, recall that a equals log base 3 of 10, so substitute a to get the interval for a. Let us wrap up with a short summary. We will process the given logarithm problem, following the exact algorithm shown. First, display the word example. Then, show the problem statement in bold orange math. Step 1. State the given relationship between a and a. Step 2. Take the logarithm of both sides. Step 3. Convert the radical to a fractional exponent. Step 4. Apply the power rule of logarithms to pull the 1/3 out front. Step 5. Substitute the given value of log a using bar notation. We interpret bar 8.7439 as -8 plus 0.7439. Step 6. Adjust the characteristic to make division by 3 simple. Replace -8 plus 0.7439 with -9 plus 1.7439. Step 7. Divide each part by 3 to get -3 plus 0.5813. Step 8. Write this as bar 3.5813, meaning the characteristic is -3 with a positive mantissa. Step 9. Use the characteristic to bound a. With a characteristic of bar 3, a lies strictly between 10 to the power -3 and 10 to the power -2. To summarize, we rewrote the cube root as a fractional exponent, applied the power rule, handled the bar notation carefully by adjusting the characteristic, and then used the characteristic to produce the numerical bounds for a. Practice this workflow with other roots and different bar logs. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.